Hey, welcome back everyone. This is John here for another tutorial, and today we'll continue to exploit our practice target that we have developed in the last video. Last time we used AFL to fuzz a simple 64-bit Linux program, and we found out that some inputs will actually crash the program. So the next step is to analyze this crash to see if it's exploitable. To do this, we'll introduce PEDA, which stands for Python Exploit Development Assistance. PEDA is a helper script for the GNU debugger, also known as GDB, and it facilitates a lot of the common techniques used for research and development. It also automates a lot of the calculation that were previously done manually. So as such, PEDA is really a nifty tool to know, and we'll briefly introduce it in today's video. So first thing first, we're going to install PEDA, and we'll do so by cloning the project from its Git repository. Just use the address that's appearing on the screen right now, and I'll leave a copy in the description as well. So it takes a few seconds. Once you do this, then you just need to modify the GDB init file by adding the source peda.py line in the gdb.init file. If it doesn't exist, you'll need to create it, or just use again the command on the screen right now. And once you're done that, well, that's it, you're done. Next time that you start GDB, PEDA will be loaded automatically. So let's try it out by loading our target into GDB. And we will do so by typing GDB space fol1, and then we're going to press enter. So now GDB has loaded our target program within the debugger, but hasn't started running it yet. To start executing the program, we're going to type R, which stands for run. And as you can see, now GDB has started the program. We are being prompted for some inputs. And once we have typed them, the program ends and GDB waits for more instruction from us. So let's do something a little bit more interesting. This time we're going to run the program, but we are going to use the inputs that were generated by AFL in the last video. So this time we will use the R command, but we're also going to use the interaction and the file crash1.txt, where the file crash1 actually contains the input fuzzed by AFL, which causes the program to crash. This time we have more data printed at the screen. And as we can see, there's a segmentation fault warning shown by GDB and PEDA. So as you can see, we have quite a few odd bytes spread around the stack. So you have bytes such as A7, 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 and then you have 3333333, which is very unusual. And if you look above, you can see that the instruction that caused the segmentation fault is the return instruction of the main function. And note that when ran into GDB, the return instruction is at main plus 149. So that's important to remember for later. And if you keep scrolling up, you will see the value of the registers when the application crashed. Now pay attention at the value of the RSP register. So by this point, the RSP register should contain the return address where execution should resume. But as you can see, it doesn't actually contain any valid 64-bit address. So let's investigate what happened here. So let's look at the AFL input that we've used to see if we can find any clues about what's going on. So for this, we're going to use xthumb to display the contents of the binary file, and simply type the following command: xthumb dash capital C space crash1.txt. So the -c option here is only to display the ASCII representation of the bytes contained within the file. So after taking a look at what is displayed on the screen, you should quickly notice that some of these values are very familiar. Especially pay attention to this line over here, which contains A7, A7, 1616, and so on. These bytes are the same bytes that we've seen pointed to by the RSP register. So this is very interesting, of course, because it means that we can override the value of the RSP register via our inputs. And therefore, we can hijack the execution flow of the program and eventually execute arbitrary code. For now, let's confirm that we have full control by testing if we can put a specific value into the RSP register. And we will do this by crafting different inputs. First thing we need to know is how big our input needs to be. And this can be obtained using the wc command in the shell. So just type wc-c./crash1.txt. The -c option is to return the number of bytes within the file. And as you can see here, we have 114 bytes. So let's round it to 120 bytes for our inputs. Alright, so before moving on, we're going to set a breakpoint at the return instruction. This way, it's going to make it much easier for us to understand what's going on. And to set a breakpoint, all you need to do is use the following command: b star space main plus 149. So remember that our return address was located at main plus 149. So now, every time we run our program, GDB will stop at the return address before moving on. At any time we reach the breakpoint, we can resume execution by using R as the command. So here's what's going to happen. We're going to ask PEDA to create a cyclic pattern of 120 characters, meaning that it's going to create us an input of 120 characters that are non-repeating. This sequence will allow us to know exactly what and where in memory things are being overridden. So going back into GDB, type pattern underscore create space 120 space pat 120. So this will create a cyclic pattern of 120 characters and store the result into a file called pat120. And if you want, you can actually go back into the shell and look at what the pattern looks like just by displaying the contents of the file we just created. And as you can see, it's a long string of characters that follows a specific cyclic pattern. So now back into PEDA, just run the program again, but this time using the pat120 file as the input. And now we have reached our segmentation fault again. And now we can see that the values on the stack are completely different and that these values are actually part of our newly created pattern. We've seen earlier that the RSP register is getting overridden by some of the bytes of the input. Now the question is, which bytes are actually overriding the RSP register? To answer this question, we'll use the pattern search command of PEDA. And once you do so, you'll see a lot of useful information displayed on the screen. Pay attention to the line that relates to the RSP register. What this line is telling us is that the RSP register is pointing to the 40th byte of our cyclic pattern, meaning that the RSP register points to the 40th byte of our input. It also tells us that PEDA found 80 bytes from our cyclic pattern following the 40th byte pointed to by RSP. So this means that bytes 40 to 120 from our input are available to us to craft our exploit. So I chose 120 characters because that's the length of our AFL generated input. However, before moving on, we should look to see if we can make it even bigger. So I've created a pattern of 200 characters and we did the same steps as before, and I got an offset of 40 as expected, but the size increased to 160. So by having more space, we can actually use bigger shellcode later on. So now we have all the information we need to actually start crafting our payload. And this is a bit how it's going to look like. So the first 40 bytes are just going to be NUPS instructions. It can be pretty much anything because they're not going to be executed or even considered at this point. At the 40th byte, we're going to put an address we want to jump to. Of course, this address will point towards our shellcode. And in this case, we'll put our shellcode right after the address. So this is basically how it's going to look like. And just to illustrate the point, we're first going to craft a very basic input with A, B's, and C's, just to make sure that we've correctly assessed all the offsets and memory locations. To craft this test payload, we're simply going to use the printf command of the bash shell. So we're going to generate a payload with 40 A's, 8 B's, and 112 C's. So in a shell, type printf space, open quotes, %0 dot s and a, close quote, open curly braces, and 1 dot dot 40 and close curly braces, and then use the greater than character to redirect the output into a file that we're going to call test. And this is a quick and neat bash way of creating a sequence of characters. In this case, we just created a sequence of 40 A's into a file called test. And we're going to do the same thing for B's, but instead we're going to print 8 of them and append them into our test file. And then we're going to print 112 C's into the same file. And here we go. So we have our test payload generated, and you can look at it by printing out the contents of the test file. And now going back to PEDA, we're going to run our target program again, but this time using our newly generated payload. If everything goes well, we should see a bunch of A's in the stack, followed by RSP pointing to a string of B, 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 whatever. And then we should see a bunch of C's following those 8 B's in the RSP. So let's look what we got. And indeed, we have our string of B's pointed to by the RSP register. And we can also see that our string of C's is following right after. So that means that the structure of our payload is valid. Now in theory, if we resume execution of our program, we should end up at address 42, 42, 42 whatsoever. However, that's not the case. If you go to the next instruction by using the next I GDB command, you will trigger a segmentation fault error. And the reason for that is that we have supplied an invalid 64-bit address. So you may think that a 64-bit processor supports 64-bit addressing. However, for the x86-64, that's not the case. It actually supports up to 48-bit of addressing. ARM8 processors also supports only 48 bits of addressing. So that means that the x86-64 processor only supports the memory range shown at the screen. But in the previous example, we provided a memory address that was way over this. Therefore, it was invalid and created a segmentation fault error. To fix that, we'll simply provide a valid 64-bit address for the current processor, and we're going to replace the 2 most significant bytes with zeros. But don't forget that we need to use the little Indian mode, meaning that when we provide our address, we actually need to reverse the order of the bytes. So let's regenerate our test payload using the printf command. So we'll print our 40 A's again, but this time we're going to put the result in a new file that we're going to call test2. Now this is where we're going to do things a little bit differently. And first we're going to print 6 B's in order to have a valid 64-bit address for the x86-64. Then we're going to add our 2 null bytes. Note that in this case we need a \0 in order to print the null character to the screen. And then we only need to add our 112 C's to our payload. And again, you can see the result just by displaying the content at the screen. This time we're going to use the xdump command, and you can see that we have 6 B's and 2 null bytes following. So let's try out this payload to see if we're going to jump into memory. So back into PEDA, we're going to run our program with the test2 payload. And once we hit our breakpoint, we can confirm that the value pointed by RSP is now 6 B's. It is. So let's go to the next instruction. And now, unlike last time, we don't have a segmentation fault. We do, however, have reached an invalid address, which is perfectly normal because we're jumping into some unknown memory location. Alright, so now what we did is actually confirm how our payload should be structured. So at this point, we are actually ready to start generating the final payload. So to help us create our final payload, we'll be using a free Python module called Pwn-Tools. Pwn-Tools comes with a large library of shellcode for different architecture. As such, it's often used in capture the flags for quick prototyping of exploits. To install Pwn-Tools, you simply need to use the pip installer by typing pip install Pwn-Tools. Now there's quite a few sub-modules being used by Pwn-Tools, so that may take a while. So once you're done with this, simply open your favorite Python interpreter. I'm going to use IPython for most of these videos. And you can start using Pwn-Tools just by importing the Pwn module. Alright, now that this is done, here is how we're going to move on ahead. So this is how we're going to structure our payload. The first 40 bytes of our payload will be filled with NOPs, or if you prefer, no operation instructions. It could really be filled with anything because we're not going to use them anyway. But putting NOPs is usually harmless. Next, we're going to put our jump address. So this will be 6 bytes representing the address we want to jump to, which will be the location of our shellcode, followed by 2 null bytes, and then we'll put our shellcode into it. Note that we're going to prefix our shellcode by a NOP sled. This is just to give us some slack in order to reach our shellcode. And you'll see why this is actually very important at the end of this video. Alright, so let's start with the first part, which is the 40 NOP instruction. So in Python, after importing the Pwn module, we'll first generate one NOP instruction using the ASM function, which basically take an instruction and return the opcode associated with it for the specified architecture. So in this example, we use the ASM comment with NOP, which is the mnemonic for the no operation instruction, and we are specifying the AMT64 architecture, and this will return the NOP opcode for 64-bit processor, which is 90. And to create a chain of 40 NOP instruction, we simply have to multiply it by 40, and we will store it in the NOP1 variable. Okay, next we'll generate the shellcode part of our payload, and for this we'll be using the shellcraft submodule of Pwn-Tools. So for this tutorial, I chose to print hello and then exit the application as payload. It's kind of lame, but it's easy and it's perfect for an introduction. In future videos, we'll use more useful payloads. But for now, just bear with me and we'll use these simple shellcodes. However, if you want to move ahead and explore more useful payloads, you can use the help command along with the shellcraft module to read more about the different things you can do with it. So just use the help function along with shellcraft and the specific payload you want more information on. This will tell you what parameters it expects and how to use it properly. So in our case, we would be using the echo function for Linux and AMT64. So if you want more information about it, just type the instruction at the screen, and we'll be using the exit function also in order to exit the program cleanly. Without it, it's just going to crash once it has finished with the echo part of our shellcode. Okay, so first thing before we start generating our shellcode is that we want to tell Pwn-Tools that we are working in a 64-bit environment. And for this, we'll be setting the context.arg variable to AMT64. So even if you are under a x86-64 architecture, within Pwn-Tools, always use AMT64 for any kind of Intel-based 64-bit architecture. Alright, so now let's generate the echo part of our shellcode by using shellcraft.amt64.linux.echo, and we're going to use hello or any kind of message as the parameter. And then we're going to append the shellcode for the exit function. So notice that we are using plus equal here. So within Pwn-Tools, you can actually concatenate shellcodes together to create your payload. Now, if you want to look at what it looks like, just use the print function with your shellcode, and you will notice that it actually generates assembly instruction. And this is what your payload will look like in memory. So of course, we're not going to put assembly instruction directly into our payload. We first need to convert this into opcodes. And to do that, we'll use the ASM function that we've used earlier to convert one up instruction into opcode. So just use the ASM function using our newly generated instruction as the parameter, and store the result into the S code variable. And if you want to see the result, just print the S code variable, and you'll see that our instructions have been converted into opcodes, which is the bytes that we will be sending as input to our target. And that's it for the shellcode part of our payload. Now, we are reaching the trickiest part of the entire video, which is to figure out where to jump to in memory. While we are working in GDB, this won't be an issue. But once we're trying to make our exploit work outside of GDB, you'll see why this is tricky. Anyway, for now, we know we need to place our shellcode where the C's are in memory. And we already obtained this address in PEDA earlier. So if you go back a little bit earlier when we tried to run our previous test payload, you'll notice that the string of 112 C's starts at address 7F, FF, 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 D, E, D, 0. So the only thing we need to do at this point is to include this address as our jump into our shellcode. So back into Python, we'll first use the struct module. So import it using the import struct instruction. Then let's define the variable a to contain our jump address. And then we'll need to convert this value into a byte array. And for this, we'll use the pack function of the struct module. So as the first parameter, we'll use the format we want. in this case lower than capital Q, and as the second parameter we'll use our A variable. So for those of you wondering what the format string means, the first character, the lower than symbol, means that we want the address in little endian format. The capital Q means that we want the value converted into an unsigned long value. So basically an unsigned 64-bit value. If you want more information about the pack function, I'll leave a link in the description of this video. And as you can see, we now have our address into a byte array. So now let's put everything together. So we'll store everything in the variable called payload. We'll first have our 40 nubs, then we'll put the address, and then we'll put a nub sled of 16 nubs, and we will then concatenate our shellcode, and that's it. We now have our complete payload built. So now what we'll do is that we'll save this into a file and run it into GDB. Note that Pwn-Tools actually have the functionality of interacting directly with GDB from your Python interpreter. However, I'm going to leave this for another video later on. For now, we'll just dump everything into a file and run it in GDB as we did previously. All right, let's do this again. This time we're going to run using the test3 file. And as usual, we are going to break at the previous breakpoint that we've set up at the return instruction. This is a good opportunity to look up ahead and see what's going to happen. So one of the first things you'll notice is the values on the stack, which now contains our payload. And if you go up a little bit and double check the value pointed by the RSP register, you'll see that it has the DED0 address, which actually points to our nub sled. So far, everything looks good. So let's confirm that everything works by using the continue command, or just type C for short. And ta-da, we got it. So we have our payload that got executed. As we can see, it printed hello, and then it exited without any errors. So at this point, congratulations, you have a valid exploit working. The only issue is that it's probably only working in GDB. Let's try it out directly on the shell. So we'll use our program and use the latest payload. And when we try to execute it together, we get a segmentation fault. Okay, so what happened here? Well, many things happened. The core cause of this segmentation fault is that the address we're trying to jump to has become invalid outside of GDB. There can be many reasons for that. One of the first one you might want to check is make sure that you have ASLR disabled on your operating system, meaning that you disable address randomization. So by default, nowadays many systems just randomize where your program gets loaded in memory. So every time you try to execute this exploit, the stack is nowhere near where it was when you ran it into GDB. And to demonstrate this, I made a slight modification to our original program. So every time it's run, it will display the address contained in RSP. And as you can see, it's different for every run. That's because I have ASLR enabled. So for now, let's disable it. And to disable ASLR in Ubuntu kind of Linux, you simply need to store the value 0 into the file /proc/sys/kernel/randomize_va_space. And you'll need root access to do so. And now, if we run our program again, you'll see that randomization of the base address of the program is always the same whenever we run the program. So that's one problem solved, but if you try again to run our exploit, you'll likely have another segmentation fault. So we're not out of the woods yet. So another issue you're likely to meet are environment variables. So when you run an application in Linux, the shell's environment variables are loaded on the stack. And when you run the program into GDB, GDB adds some environment variables before executing a program. Therefore, the stack offset between running the program in the shell and in GDB is actually different. So if we execute our program with the environment variables, we see that the stack is located at DEE0. Now we'll execute it without the environment variables, and we do this by prefixing the comment with env space dash. So that will specify to the shell that we want to execute our program without the environment variables. And as you can see, the stack is now starting at ED70. One temporary solution for this is to run the program both in GDB and in the shell without using any environment variables. This way, we will limit the influence that environment variables have on the location of the stack. So we already shown how to execute the target program without any environment variables. To have the same effect in GDB, you're going to use the onset space env comment at the beginning, so before you actually run the program. So this will tell GDB to onset any environment variables currently defined. So of course, if you find a new address, you'll need to modify your Python code and regenerate your payload in order to continue your tests. And that's why you want to develop Python code that you can reuse over and over again. And I'm going to share mine with the article related to this video. And despite all of this, your exploit still may not work. One of the reasons is that GDB might still be adding some instructions when it's debugging your application. At this point, the only thing left to do is, unfortunately, trial and error. Meaning that you're gonna increase your nub sled in front of your shellcode and modify your jump address by a few bytes and attempt to execute your exploit in the shell and hope that it works. However, at this point, fortunately, we remove most of the variables. So it might only be a question of trying a few times to get it right. In my case, when everything was done, I actually had to increase the jump address by 140 bytes and increase my nub sled to 80 bytes. In your case, it might actually be very different depending on your operating system and many other things. So this is where the art of software exploitation comes into. It's a mix of trial and error, experience, and sometimes it's just pure luck. Alright, so I'm going to stop here for today. Depending on your level of experience with software exploitation, this video was packed with quite a few new things. And to be honest, we're barely scratching the surface of it. As you probably realized during the videos, we actually disabled quite a few security mechanisms to make our exploit work. And furthermore, our target program is quite simple really, there's nothing to it. And we use a pretty simple and lame payload. However, my goal really was to introduce you to the generic process used for software exploitation. So first, we fuzz our target program using AFL to detect any potential crash leading to a vulnerability. Then we use GDB and PEDA to analyze the crash and see if we could potentially exploit a vulnerability. And then we use Pwn-Tools to create a payload and a working exploit for our target program. And this is a process we're going to use many times over when we will target a new program. So there's still a lot more to learn in software exploitation. So in the upcoming videos in this series, we will keep learning about the tools that we have introduced so far, learn about new techniques to defeat some of the memory protection that are usually present nowadays, and just keep practicing in order to become better at it. This is the key of everything. And that's all for today. If you have any question or additional information, leave a comment below. Also, if you have enjoyed this video and learned something, please consider leaving a like or subscribing to my channel. Thank you for watching, and see you next time.